Hello everyone and welcome to this long overdue lecture where we try to find a better understanding of the diagonalization process of a matrix. So let's start. And just like almost everything else in linear algebra, our journey will start with a matrix. As you can see, I have chosen the simplest matrix in the history of matrix and also in the history of simplicity. And we want to diagonalize this matrix. But you already know how to do that, right? You find the characteristics equation, you solve it for the real values, and then, which gives you the eigenvalues, you find the corresponding eigenvectors for those values, and that will give you enough information to find the diagonalization, which is this. We have the matrix P, which is basically the columns of, the eigenvectors as the columns. We have the matrix D, which have the eigenvalues as its diagonal. This is a diagonal matrix, hence the name diagonalization. And then at the right hand side, we have the inverse of P matrix. Right? Pretty simple. The math is very straightforward, basic algebra, and to be honest, a little boring. But I think the real question that we all should be asking here is, what on earth did you just do? And why? Well, to answer that question, let's first talk about the diagonal matrix itself, shall we? We shall. So this is a diagonal matrix. How can you tell? Well, all the non-zero elements of this matrix are along the main diagonal. That is the definition of the diagonal matrix. And as you can notice, all the other values are zero, which right off the bat makes any calculation involving this matrix a whole lot easier. For example, if I want to take the nth power of this matrix, all I have to do is take the nth power of each element along the diagonal, which also means if I want to take the inverse of this matrix, all I have to do is take the inverse of each element along the diagonal and done. Well, taking the inverse of a matrix is pretty hectic work, so this is very convenient, right? I'd say it's a convenient thing. And if that was not enough, well, matrix transformation using diagonal matrices are way easier, just so very simple. Allow me to demonstrate that using an example. So think about your company, and this is the simplest company in the world we are talking about, because every year the cost and revenue of this company just increases by a certain constant factor. So as you can see, in this case, the cost of the company every year increases by 40%. So the new cost is 1.4 into the old cost, and the revenue increases every year by 80%. So apparently this is also the best company in the world to invest in, if I had the money to invest. Anyway, so if we can very easily express these two equations using a matrix vector multiplication. So let's do that. And here is our matrix vector multiplication. This is our matrix, and you may have noticed this is a diagonal matrix. This is our cost revenue vector. Multiplication will give me the new cost and the new revenue of the new year. And this relationship also tells me that if I keep multiplying this matrix over and over again, I'll keep getting the cost and revenue of each successive year. For example, if I want to know what happens 1,000 years later from now, I'll just have to take the 1,000th power of the matrix. And as this is a diagonal matrix, taking the 1,000th power is not a very difficult task, right? So let's look at this graphically. That will give us a better understanding, I hope. So we have the x-axis, which gives us the cost, represents the cost. We have the y-axis, which represents the revenue. Let's just assume everything is in the unit of $1 million. So 1 is $1 million, because why not? So this is our vector at the beginning. We have the cost $X million and our revenue is $Y million. And this is our matrix. I've just put it here to keep track of what we're doing. So after the first year, the cost is going to be 1.4x and the revenue is going to be 1.8y, right? That is the relationship we established. And after the second year, this is just going to be 1.4 square, because we are going to multiply 1.4 one more time with cost. And the revenue is going to be 1.8 squared into y, because we are multiplying 1.8 one more time. And as you may have guessed, after 1,000 years, this is just going to be 1.4 into to the power 1000 and 1.8 to the power 1000. This is very straightforward and very simple to imagine and even to calculate, right? Because the transformation matrix that we're using here is just a diagonal matrix, and all the transformation that is occurring is just scaling. The x-axis is being scaled by a factor of 1.4. The y-axis is being scaled by a factor of 1.8, which is pretty simple and not really much to discuss here. Anyway, so now let's think about a company which is not as simple. It's still simple enough for a company, but just more complicated than the last example we had. So the cost-revenue relationships are a little more complicated here. So to get the new cost in the new year, you have to take the old cost with a 20% increase, and with that you have to add 50% of the old revenue for some reason. And to get the new revenue, you have to take the old revenue, and that will be increased by 20%, and you'll also have to take the old cost, 50% of the old cost. So let's say, for example, this is our cost-revenue relationship. We can also express that using a matrix vector multiplication, and if you look very closely, very carefully, and give proper attention, some of you may even realize that this matrix is not a diagonal matrix. I know, right? Anyway, which means if I want to know what happens after 1,000 years, I'll have to do this, but this is going to be much, much more difficult because a matrix multiplication is not fun at all. Now, this is a 2x2 matrix, as I said, the simplest matrix in the history. So taking the 1000 power of this matrix is not that big a deal. If you ask a computer, hey computer, do this for me, the computer will probably go like, yeah, sure, why not? But in real life scenarios, in most cases, you will probably be dealing with data as large as a 500 million by 500 million matrix. And if you ask your computer to do that, your computer will probably burn your house down. So I think we can all agree that this is a bad news. We really don't want to do this. And that is why we do diagonalization. But later on that, let's first look at the graphical representation of all this to see exactly how bad it is. Just like before, this is our xy plane. X-axis represents cost, y-axis represents revenue. We are at the very beginning at $X million cost and $Y million revenue. This is our very non-diagonal matrix. So what happens after the first year? This is what happens after the first year. I have kept the original x's so that you can understand what's happening. The transformation will shift the whole interspace into something very uncomfortable. And that is just after 1 year. Multiply this matrix again. After 2 years, it is looking bad. And this is getting out of hand so very fast. As you can see, I don't even want to think what happens after 1,000 years. So this is a problem, right? But if you notice, even in the middle of all this chaos and all this mayhem, there are two very special vectors who are like, meh, they don't care, they're chilling. And those two vectors, some of you may have guessed, are the eigenvectors. So we have our eigenvector 1, 1, with the eigenvalue, corresponding eigenvalue 1.7. We have the eigenvector -1, 1, which have the corresponding eigenvalue 0.7. So let's see what happens. Let's do the simulation again and let's see what happens to these vectors. So after 1 year, the eigenvectors are just going to be scaled up in the case of this and scaled down in the case of this vector. So that's all that happens. And in the second year, the eigenvectors are just going to be scaled up by a factor of 1.7 again, and this eigenvector, this one, is going to be scaled down by by the factor of 0.7 again. So as you can see, these two vectors, only these two vectors, like vectors along these two lines, they don't care. They are barely affected by this transformation. Everything else is just all over the place. They are changing direction. They are just going from, I don't know from where to I don't know from where either. But these two vectors, They are not changing directions because that is the definition of eigenvectors. They don't change direction, they just scaled up, they just scale up or scale down or just remains the same. So these two vectors are so powerful in the context of this particular matrix that they are barely affected. They are only being scaled up or scaled down, which was the case for all vectors in our last example. All vector, everything was being scaled up, everything along the x-axis and y-axis, so our standard axis. In this example, the same thing is happening to the eigenvectors. Even our x-axis and y-axis are being changed, so they are also affected hugely, which makes you think, if we could map everything else using these eigenvectors, these mighty, powerful, not changing, unwavering eigenvectors, that would be really very, very helpful, right? Only if we could do that. But if you recall anything from matrix transformation, you will know that we actually can do that. Whenever we apply a matrix transformation to a space, the space is transformed. Well, yeah. And every vector is being mapped to some other vector. So let's see what that looks like, just to refresh our memories. So this is our original space. Identity matrix keeps things as they are. So a 45-degree rotation, the space is shifted. All the vectors are being mapped to a vector that is 45-degree counterclockwise to it. This is a scaled version of the space. This is another rotation. This is a shear. So the matrix transformation is changing the space. The vectors are being mapped to other vectors. The x's are being changed. So there must be some transformation. We can just, only if we can find one transformation that will map the eigenvectors to our standard basis vectors, in other words, to our standard x-axis and y-axis, that would solve, even if not solve, that would really make things easy for us, right? And that is exactly what diagonalization does. This part of the diagonalization, the p-inverse part, it changes the standard coordinate system that we are familiar with. So our standard basis, I hat and j hat, it changes that coordinate system and maps it to the eigenvectors. This is the job of that part. If you don't believe me, let's look at it. So this is the same space. The green vectors are I hat and j hat, our standard basis vectors. The golden one are, is it yellow? Who cares? I don't. Anyway, so the green ones are the standard basis. The golden ones are the eigenvectors, right? So let's just take a random vector. This is going to be our example, the vector 4, 2. So the coordinate 4, 2 means if I go 4 times along the first basis vector, the first vector of the basis, that is I hat, if I go 4 times this, and then if I go 1 times this, I'm sorry, this is not properly scaled, I'll reach here, right? So the relationship is expressed by this equation. Now I claimed that the P inverse matrix will convert this coordinate system and map it to the eigenvectors. So let's multiply that P inverse matrix with this coordinate system, and it gives me a new coordinate 3 minus 1. And if you check, if you go along this vector 3 times and then go along this line minus 1 times, so which means opposite direction, you will reach here. Again, sorry, the vector is not properly scaled, but you can verify that using the algebra. 3 times this vector plus minus 1 times this vector, you reach this point, this 4, 2 point. So P inverse matrix is actually converting our standard coordinate system to something that is expressed by the eigenvectors, in respect to the eigenvectors. And that is precisely what we wanted. So this is our original matrix that we are dealing with. This is any random vector. We can diagonalize this as P d P inverse, and this part right here, this part is converting the standard coordinate system to something with respect to the eigenvectors. And when everything is in respect to the eigenvector, we know the eigenvectors are only being scaled up and down, so that is what's happening here. We don't have to concern ourselves with all the other chaos that is going on. We just know the eigenvectors are only being scaled up and down by these vectors, 1.7 and 0.7. So that is happening. All the main work is happening here. And when that is done, we cannot just stay in this coordinate system, because this is not the standard system. Everyone, everywhere in the world uses the standard coordinate system, right? So we have to go back to that. And this is that part. So this part is converting our xy coordinate to the eigenbase. And this part is doing all the work. And then this part, please note that this is just the inverse of this part. So this is just changing back to standard coordinate system. So this is the neat trick of diagonalization. Whatever we are doing, we are changing back to a convenient system for our own convenience. And then we are doing the transformation, but this time this is just diagonal matrix. So this is a lot easier. And when we are done, we are going back, just changing everything that was changed by this, changing back everything. And the beauty of this is, if I do this 1,000 times or 10,000 times or 2 times in this example, we don't have to do this over and over again, because if you notice, these two cancels each other out, because the effect of P and P inverse are just opposite to one another. So these two cancels each other out. So this is a square, right? So we are changing back to eigenbase, we are changing back to eigenbase once, and we are applying the transformation as many times as we require. And once we are done, we are changing back to the standard basis. So if we want to do it n times, change to whatever it is, what is it called? Change to the eigenbase. From the standard basis, we are changing to the eigenbasis. Doing this n times, so d to the power n is very easy to calculate. A to the power n is not very easy to calculate. So we are doing the easy stuff, and when we are done with the easy stuff, we are just changing back to the standard basis. That is what diagonalization is all about. I hope that was helpful. Could be a little confusing, and if you're confused, I'm really sorry, but I think just watch the video again, I think. Anyway, I hope that was helpful, and I'll see you. Actually, the next topic is next semester, so I might not see you again. Anyway, thank you for watching the video, and good luck. Goodbye. Sorry, I meant to say goodbye. I'm not sure why I said goodbye.